All right, so yeah, on page 3 of your guided notes, it explains different ways. Can I borrow yours for a second? To calculate enthalpy. To, to calculate the change in enthalpy, this is the difference between the potential energies of the products and reactants. So oftentimes we talk about enthalpy as being like the heat of reaction. So it can be calculated several ways. One of the ways is through stoichiometry. Okay. Another way is through calorimetry. Another one is from tables of standard values using what I call the Big Mama equation, the enthalpies of formation of the products minus the enthalpies of formation of the reactants. Another way is through Hess's law. And then the fifth way, we're actually going to learn it in a much later unit, that's through bond energies. Okay, once we go over Lewis structures and review that, we'll talk about bond energies. So there are 5 different ways to measure, or sorry, to calculate enthalpy. They're not interchangeable. It's not like when we were talking about doing stoichiometry versus the dilution formula for acids and bases. You can do either one, and you'll work. You have to know all of these methods because it really depends on what is given in the problem. That dictates what method you'll use to solve for it. Okay. So the first way we're going to talk about, we're only going to talk about stoichiometry and calorimetry today. We'll do Hess's law and the Big Mama formula in 2 classes. Okay, and we'll do bond energies in a later unit. So for today, let's talk about stoichiometry. So we have this reaction, the combustion of propane. What do we know about combustion reactions? They're extremely exothermic, and we can see that by the given delta H value. It's negative, that means it's exothermic. Okay? So what this means is this is the amount of heat, so the 2,221 kilojoules of heat are released when we burn 1 mole of methane. And it's released because it's negative. Why do I know that that's per mole of methane? Because the coefficient in front of methane is 1. Okay? If when this was balanced and there was a 2 in front of that methane, and then I gave you that delta H, then it might be for 2 moles of methane. So it's like per mole of the whole reaction. Okay? So in order to do stoichiometry with this, we're told that we're assuming that all of the heat comes from the combustion of propane. We're going to calculate the delta H in which 5 grams of propane is burned in excess oxygen at constant pressure. So what do I do first? Convert grams to moles. So I need the molar mass of methane, right? Yep, you should get just over 44 grams, okay? And now, so this would tell me how many moles of methane I'm burning. Or sorry, not methane, propane. That's how many moles of propane I'm burning. Well, now I'm going to figure out what's my kilojoules for that mole, okay? Or for those moles. So I can actually just put this in my stoichiometry. Yes, I know I just put a negative in a dimensional analysis stoichiometry problem. That's perfectly acceptable when you're talking about energy. Because all that negative tells us is that energy is being released. Okay? So what do you get? Negative 252 kilojoules. All right, number 9. The enthalpy for the formation of Na2O is shown below. We're given the equation, and we're told the delta H for that equation, as balanced, is negative 828 kilojoules. We want to know what is the amount of heat released when 1 mole of Na2O is formed. And we're going to make this 1.00. I think I already did that on your paper, but I'm not sure. All right, so when we have 1 mole of Na2O formed, how much heat is released to form that? Okay, so last problem, our first step was to convert from grams to moles. I'm already in moles, so I'm just doing moles to kilojoules, right? So 1.00 moles of Na2O. Now I'm going to put in my delta H value. Well, what goes on the bottom? 2 moles of Na2O. Where did you get the 2 from? The coefficient. Because this value was for this entire equation as balanced. Okay? Just be aware that sometimes it's not a 1 on the bottom. So what do you get? What? Yep, negative 414 kilojoules. Cool? So just keep in mind that when you're doing these, that just read the problem carefully, okay? All right. Number 10 is actually really easy. There's no calculation involved. So we have the enthalpy for the decomposition of Fe2O3 is shown here in that first equation. And then what is the enthalpy change for the following reaction? What do you notice about the two equations? They're opposites, right? Yeah. So in the first equation, Fe2O3 is my reactant, and it's producing these two things. In the second one, these two things are forming the Fe2O3. They're just opposite equations. Okay? So we flipped the equation. If the decomposition of Fe2O3 requires 472 kilojoules of energy, then the formation of Fe2O3 would do what? It would release 472 kilojoules of energy. So my delta H for this second reaction is what? Negative 472 kilojoules. Okay? So when you flip the reaction, you flip the sign. And we're going to see more of that in 2 classes when we go over Hess's law. Okay, this is one of the bases of Hess's law. When you flip the reaction, you flip the sign. Okay? Cool? All right. Number 11. We're going to determine the amount of heat released at constant pressure when 1 gram of ethanol, C2H5OH, is combusted in excess oxygen. So this is still more stoichiometry. Anytime you do stoichiometry, what do you need? A reaction. So, in writing this reaction, what are my reactants? What are my products? Carbon dioxide and water. How did you know it was carbon dioxide and water? Because it's a combustion reaction. So now what do we need to do with this equation? Balance it. Take a moment to balance this. I'm going to pause it while you do that. All right, so when this is balanced, what are our coefficients? 1, 3, 2, 3. Good. All right, now to actually do the math with this problem. With the previous problems, like with this one, I gave you the delta H value, right, in the problem. This one, I forgot to do that. Oops, too far. So the delta H for this reaction, for 1 mole of this reaction, is negative 1275 kilojoules. Okay? So now we could just do the stoichiometry like we were doing before. Why don't you guys try that one? Now that you have all the pieces of information, try the stoichiometry on your own. And I will pause it while you do that. All right, so I'm just going to quickly put the math up here since you've already done this. So we have 1 gram of ethanol. We're going to have to convert that to moles. The molar mass of ethanol is 46.08. And then we're going to multiply that by the enthalpy. And we should get negative 27.7 kilojoules. Cool? Yeah. It should be. Yeah, it's recording. Okay, cool? All right, so that's stoichiometry. That's finding enthalpy or using enthalpy in stoichiometry. The second way is calorimetry. Okay? Calorimetry is using this formula. Q equals MCAT. Q equals MC delta T. Q stands for what? Heat. M is mass. C is the specific heat capacity of a substance. That means it's the amount of energy required to raise the temperature of 1 gram of that substance by 1 degree Celsius. Okay, so it's a constant. It's a standard value. You'll either be given it or you have to solve for it. There's one you have to memorize, and that's for water, because water is very ubiquitous. Okay? And then delta T is our change in temperature. How do we calculate delta T? Final minus initial. Good. All right. So for number 12, we're going to be calculating how much heat must be added to change the temperature of 250 grams of water from 25 degrees Celsius to 60 degrees Celsius. So if heat must be added, what does that make this process? Endothermic. Therefore, what should we calculate Q to be in terms of its sign? It should have a positive sign. So, like I said, these are things to help you along the way so that, does my answer make sense? If you get a negative Q, you've done something wrong because it should be added. Okay? So mass is what? 250 grams. C for water is 4.18 joules per gram degree Celsius. Like I said, I do want you to memorize this. And then delta T is always final minus initial. We're ending at 60 degrees Celsius, and we're starting at 25 degrees Celsius. Just water. That's the one I want you to memorize. All right. Nope, just water. Just liquid water. And what do you get as your Q? Is it positive? Yeah, I hope so. And how many sig figs will we have? Two. So what do you get? And that's joules. Unless the problem specifically asks for your answer to be in a certain unit, you can leave it in whatever unit the formula calculates it as. Like here, it's going to calculate it as joules because our specific heat of water is in joules per gram degree Celsius. So whenever you use Q equals MCAT, it's going to spit it out in joules, unless it specifically asks you to convert it to kilojoules, or unless you have to then use it later where you need it in kilojoules, leave it in joules. Don't waste your time and risk making a careless error by converting it, okay? Because I have not seen, I might have seen this before, where somebody calculated this, 37,000 joules, and they're like, oh, that's 370 kilojoules. It's not, it's 37 kilojoules, but then they box both answers, and I'm like, one's right, one's wrong, I couldn't give them the point. Or they lost points. Even though they did have it right, but then because they converted it incorrectly, they lost the point. And I know that that's happened on the AP exam before. Okay? All right. And what sign does this have? Positive. Because it's being released. Or, sorry, it's being added. Sorry. It's being added. It's endothermic. Okay? So let's do some more with Q equals MCAT. So for this one, this is just showing you different things you can solve for. We have 2.09 joules are required to change the temperature of 15.0 grams of mercury by 1 degree Celsius. And we're going to calculate the specific heat of mercury. Is this process endo or exo? Endo, because energy is, or heat is required. Okay, so Q equals MCAT. This time we're solving for C. My Q is 2.09 joules. M, what's my mass? C is what I'm solving for. And delta T is what? 1 degree Celsius. So go ahead and do that quick algebra. And the C of mercury is what? Yep. 0.139 joules per gram degree Celsius. Now let's compare that to water. Let's compare that to the specific heat capacity of water. What was the specific heat capacity of water? 4.18, right? Because you already memorized it from the last problem. So 4.18 compared to 0.139. The size of the C value will tell you how much that substance will change temperature. The larger the value, the more energy it takes to change temperature. So if I were putting the same amount of energy into both my mercury and my water's temperature is going to change less because its specific heat capacity is greater. Now, that's if, say you have the same amount of both water and mercury, you put the same amount of energy into both, because water has a higher specific heat capacity, its temperature will change less. Mercury is going to change a lot. Metals typically have very low specific heat capacities. This is what makes them great thermal conductors, because they're going to change temperature very easily and transfer heat easily. Okay? Have you ever cooked, like put something in the oven and you covered it with like aluminum foil? When you take it out of the oven, you can touch that aluminum foil almost immediately, because it has a very low specific heat capacity. It isn't going to transfer that heat very well. Or, sorry, it's going to transfer, it's not going to, I was thinking ahead of myself about what I wanted to say next, and then I tripped over my words. It's going to change temperature very, very easily. And also, aluminum foil is very thin, so its mass is very, very, very small. A big, heavy pot that's metal, it's very heavy, so its mass is great, so it's going to retain that heat more just because there's so much more of it. But its heat capacity is still very low. Have you ever been to... Have you ever been to the beach at like the beginning of summer and then again at the end of summer? Yeah? What? Okay, not the same beach, but so have you ever been to like a beach in like maybe June? The water's kind of cold, right? Versus if you go in like September, that water's nice and warm. Okay, that's because water has a very high specific heat capacity. It retains that heat. It takes a long time for it to warm up, but then it takes a while for it to cool back down as well. That's why I like going to the beach like in August, September time frame, because that water's nice and warm. Even though the air temperature might be dropping, the water temperature isn't dropping as fast. Okay. All right, so what I wanted to say here is C is inversely proportional to how much temperature will change. So the larger the C, the smaller the temperature change. Keeping everything else constant, keeping joules and mass constant. Comparing just C to delta T, they're inversely proportional. Okay? All right. So for number 14, we're going to be calculating the final temperature after 1575 joules of heat are removed from an 85 gram sample of ethyl alcohol that's originally at 25 degrees Celsius. And I've given you the specific heat of ethyl alcohol. So, Q equals MCAT, right? What's my Q value with proper sign? Negative 1,575. Why is it negative? Because what? Why do we know it's exothermic? Because heat is being removed. So that makes it exothermic. Okay. What's my mass? 85 grams. My C is what? 2.4, and that's joules per gram degree Celsius. And I don't know delta T because I don't know T final. T final is what I'm solving, but I know T initial to be 25. Okay. Before we do the math, let's talk about our answer. Heat is being removed. That means how will T final compare to T initial? T final should be lower. Our temperature is decreasing. Plus, the only way for this to be negative is we have to have a negative somewhere here. Mass can never be negative. C can never be negative. So it's got to be that delta T that's negative, and the only way for delta T to be negative is if T final is smaller than T initial. So my prediction is that T final is smaller than T initial. So when you're doing the math, if you don't get a smaller number, you've done something wrong. Maybe you just dropped the sign originally. Or maybe you typed something in wrong. You did your algebra incorrectly. What'd you guys get? Yeah, just 2 sig figs. Because of the, well, both the initial temperature and my heat capacity. So, 17 degrees Celsius. Cool? Which is lower than 25, so we can safely assume that we did the problem correctly. And it makes sense, too. The temperature is not going to drop like 1,000 degrees. Okay? It's going to drop a few. All right. Now let's talk about this one. So number 15, we have an unknown metal that has a mass of 28.4 grams. it was heated to 110 degrees Celsius. And then it was immediately plunged into 100 grams of water. The water was initially at a temperature of 24.60 degrees Celsius. The final temperature of that mixture, the metal piece and the water together, raised to 25.43 degrees Celsius. And then we're going to calculate the specific heat of the metal. We're actually not going to identify it because we don't have a chart. But so here's my beaker. Here's my hot metal. And it immediately gets plunged into my much colder water. Right? So let's think through the problem. What can be said about the heat of the metal?
It's going to drop.
Yeah, the Q of the metal should be what sign? Negative, because it's decreasing temperature. It's going from 110 down to 25.43. Okay? So the metal is doing what with energy? Is it gaining or losing? Losing. It's losing heat. So the Q lost by the metal, that should be negative, right? And then the water is doing what? It's gaining. And that should be positive, right? Now, what can be said about the Q lost by the metal and the Q gained by the water? They should be equal in magnitude, right? So if we take the absolute value of both of them, they should be equal. Assuming that none of the heat was lost to the surroundings. The problem didn't state that, but we can assume that for right now. Okay? Plus, we weren't given any information about how to calculate the amount of energy lost to the surroundings. That's a later problem. Okay? But assuming that all of the heat stayed trapped within the water once they mixed together, none of it, went out the top or the sides, then all of the heat that is lost by the metal is going into the water. Law of conservation of energy. Doesn't just disappear. Okay? So, what formula do we use with Q and C and all that stuff?
MCAT.
Q equals MCAT, right? So we could do Q equals MCAT twice, or make it easy on ourselves and say negative MCAT equals positive MCAT. Okay? Where negative MCAT is going to be all of our metal information. It's negative because our Q is negative. And positive MCAT will be all of our water information. It's positive because its Q is positive. So now we can just plug in. It's going to be a lot of algebra here. So, negative. The mass of my metal is 28.4 grams. C is what I'm solving for. That's my unknown. My delta T for the metal is, its final temperature is 25.43, and its initial was what? 110. And all of that will equal, what was the mass of my water? 100 grams. Oh, add in a sig fig. What is C of water? 4.18. And my final temperature for my water is the same as the final temperature for my metal, 25.43. And what did my water initially start at? 24.60. Okay? So now this is a lot of algebra here. Take a moment to go through it all, okay? Actually, before we do that, let's predict our answer. Let's predict our answer. Notice that the metal's change in temperature is significantly larger than the water's change in temperature, right? And we also have a lot less of the metal than we do of the water. So do we think our specific heat of the metal will be greater or less than that of water? It should be less because it changed temperature a lot more. Remember, they're inversely proportional. So our prediction is C of the metal should be less than C of water. So take a few minutes to go through all that algebra because it is quite a lot. I'm going to pause it while you guys do that. All right. So when you do all the algebra, you should get 0.144 joules per gram degree Celsius. You should get that. If you got a little bit off, if you got like 0.143 or 0.145, like a little bit off, it's probably just from maybe you rounded earlier on or something like that. If you got significantly off, then you might have done something wrong. Some people were saying that they subtracted 100 here as opposed to 110. They used the wrong T initial for the metal. Okay? But if you're like way off and you have no idea what your issue is, come see me during office hours. Okay, we can go through the algebra of it. All right, I just want to do a couple more. I'm not going to get through a lot more, but I just want to do two more real quick. Number 16 is actually really quick. Look in here. So we have a 100-gram sample of water at 90 degrees Celsius, and that's added to a 100-gram sample of water at 10 degrees Celsius. And we're going to figure out what the final temperature of the water is. But first, let's discuss what we know about our two samples of water. What can be said about their specific heat capacities? They're the same. Why? Because they're the same substance. So we have the same substances, therefore same C. What else can be said about these two samples of water? The same masses. So if we were doing negative MCAT equals positive MCAT, what cancels out? M and C. So to find delta T, hey, that rhymed. To find delta T, to find the final T, it's just going to be an average of the initial T's. Right? Of the two things, because it's the same mass and the same substance. If one of those isn't the same, then you cannot just take the straight average. But since both of those things are the same, 90 plus 10 divided by 2 is 50. So therefore, B would be our answer. Okay? These are great multiple choice questions. Now, for number 17, we still have water. Both of our samples are water, so it's still the same substance. But what's different? The masses are different. Now, we can still answer the multiple choice question without doing a bunch of math, okay? Because we have a 100-gram sample at 90 and a 500-gram sample at 10. So the average between 10 and 90 is 50, but we have a lot more of the 10 degrees Celsius water. Therefore, our final temperature will be closer to what? It's going to be closer to that 10-degree sample because there's a lot more of it. It kind of wins out. So our answer will be somewhere between 10 and 50. Now let's do the algebra, which you might need a calculator to do that type of stuff to confirm that. But the multiple choice part of this is a perfectly valid multiple choice question. Okay? So negative MCAT equals positive MCAT. Can we cancel anything? Yeah, we can cancel the C's. It makes that algebra a little bit easier, unlike in number 15 where we had everything was different. Different masses, different samples, different initial temperatures, everything. The only thing that was the same was the final temperature. So, now, negative MCAT is going to be the sample that's decreasing its temperature. So that's going to be my 90-degree sample, or my 100 grams. Positive MCAT is going to be the one that's increasing temperature, or the 500-gram sample. Okay. So take a second, maybe a few seconds, maybe a couple minutes. to do this algebra, calculate the final temperature. But again, it should be somewhere between 10 and 50. If you don't get between 10 and 50, you've done something wrong. All right, so when you do your calculation, you should get around 23 degrees Celsius, which is in between 10 and 50, which is what we predicted. Cool? All right, we're going to stop there today.